Hi everyone. This video is about performing artificial. Our goal here is to come up with a plan or a sequence of actions when we have uncertainty in our world. And the world can naturally be modeled using continuous variables. Alternatively, we can model the world using discrete variables, but the natural thing to do would be to use continuous variables. And we want to reach the goal, which is the essential component of every planning problem, by a reward function, similar to the way that Markov decision processes are handled. So this is a decision-making problem where the agent has many decisions, has many choices, and has to come up with the best solution. And we guarantee that our approach is exact and optimal. Note that in the literature, problems have been solved in the continuous domain approximately, or they have been discretized. And our approach would be to use logical concepts similar to the strips domain, where everything is modeled using logical components. We use first order logic here, and we provide a lifted solution to our Markov decision processes. So what problems or what domains is this applicable in? Well, any real-world problem that has uncertainty in it. For example, in the operation research literature, water reservoirs, we want to see how much water and when to drain this water so that we avoid flooding while at the same time producing energy. Or in the inventory management control problem, we want to see how of a specific item in the inventory to order to reduce the costs of the inventory at the same time being able to respond to customer demands. Or in a Mars rover problem, the rover has limited energy, power energy. So when would we want to take the pictures to come up with the best pictures and avoid wasting any of the rover's power? Or in the steam engines, we want to produce electricity, but there's steam in the system that we have to let out. So when would we want to open the valves, considering the fact that the steam causes noisy observations? Or in a telescope control problem, a space telescope has to move around to take pictures. Now, how would we control these movements to come up with the best angles? Having seen these domains, how would we solve it? Well, we follow a sequence of steps. First of all, we have to model using continuous variables. For examples, we can model our states in a water reservoir using continuous water levels. We can model the actions using continuous time to drain or not drain. And we can model our uncertainty, such as rainflow or the amount of water evaporated. Next, we define the goal. So our goal is to find a sequence of actions and to achieve the total energy, and we want to maximize this total energy. So this is done by a reward function. And we provide a lifted solution where all functions and operations are symbolic. They're in the lifted level. We have no variable groundings. And we use the fact that continuous variables have a natural bound on them to come up with a range of possible answers. For example, in the water reservoir problem, instead of discretizing or approximating, we define two levels of a multi-reservoir problems between any value between 0 and 5,000. So 0 is the minimum value that we can, and 5,000 is the fact that is defined by the fact that the reservoir is full. Now our policy would be to drain a specific amount of water in one iteration, not drain in the other. So this is the optimal policy, so that we can produce the maximum energy, and this can be done using symbolic Bellman equations. A symbolic representation of our problem is to define all functions. We can have reward function, transition function, or in the partially observable case, observation functions, and we can define them using case statements. In the example here, you can see that the function is defined by two cases. If x is bigger than 3 or if y is smaller than 3, then the partition value would be to add up x plus y. All our operators can also be defined symbolically. For example, adding two symbolic functions of f and g, we simply take the AND of the constraints, pi and phi1 and psi1, and we sum the values of f1 and g1. Similarly, maximization is trivial since you can take any two partitions and you can AND the constraints and also see if the value of f1 is bigger than g1. In that case, the maximum would be f1 and so on. Now that we have defined all our operations, all our functions, and all our variables, we can define the symbolic solution using value iteration, which is defined by Bellman in the 1960s. This is defined by a two-step algorithm. In the regression step, we simply add the current reward with the previous discounted value. Note that the discounted value is multiplied by all the possible transitions from the discrete variables of b and the continuous variables of x, and we take the sum over all possible discrete variables and the integral over all continuous variables. Next, we maximize this Q value, which is defined for each action, to come up with the best action that will lead us to the maximum value. Now, we also need an efficient data structure since, as you can see, each function can have many cases, and multiplying or taking the maximum over all the case partitions can cause an exponential blow up. So we use the data structure similar to decision diagrams, the extended algebraic decision diagram, which allows ordering and pruning and is best when we have linear constraints and can define any type of logical constraints in the nodes and also values in the leaves. So what can naturally be done in our domain? Well, we can have to wrap it up, so we define the first exact solution to many problems, such as the inventory control, which has not been solved since the 1950s. And we plan to achieve the maximum reward, which is the main goal of this planning system. And we can also handle all sorts of uncertainty and stochasticity in states and actions effects. And to reference, I have provided two of my papers that have been recently published on this subject. Thank you, everyone.